All right, so this is the first step of the scientific method. We observe things. But when we observe things, we try to be as quantitative or as qualitative as possible. Do you know the difference between quantitative observations versus qualitative observations? In other words, when we observe things, we usually take measurements. And when we deal with measurements, there are a whole bunch of things we need to keep track of. What are the things that we need to think of when we take measurements? Well, the first thing was, are these quantitative or qualitative? Quantitative, let's see, I probably should sit down, versus qualitative. And so what's the difference between a quantitative measurement versus a qualitative measurement? Well, one example of this would be like the number of people at a concert, let's say. You know, qualitatively there might be 1,000 people at the concert. Quantitatively you count each individual, and maybe there's 997, not 1,000. And so 1,000 would be much more qualitative. It's a roughly, a rough measurement or a rough approximation. Whereas quantitative, you want a more what measurement? More exact measurement. And although we don't use the word exact, we have other words for that kind of mean the same thing, like precise, more precise, or more accurate. And so when we take measurements, we got to think in terms of quantitative versus qualitative. We need to think in terms of precision and accuracy. And we need to think in terms of error. You know, whenever we take measurements, there are two types of errors that we have to worry about. What are those two types of errors? Random error and not procedural, random and systemic, not systemic, but close. Systematic. Yeah, that's correct. Systematic. All right, so let's go through some of these points. Qualitative, these are just more approximate measurements, whereas what did I do? Quantitative is not approximate. Quantitative is more precise and accurate, whereas qualitative are more approximate. More precise, more accurate. And then in terms of error, whenever we take a measurement, there's error associated with measurement. And so let's think in terms of precision here first. In terms of precision, we have different levels of precision. So for example, let's say we weighed the mass of an object. Can you guys read this over there? Not really? A little bit? Do you want to move one up, or is it adequate? Oh, okay, should I write bigger? I'll make the pen thicker. So we might measure the mass of an object, and we weigh it on one balance, we have 5 grams. On another balance, we might get 5.0 grams. On another balance, it comes out to 5.00 grams. So the first question is, which of these is more accurate? Actually, we don't know which one's more accurate. It depends on what the object actually weighs. Let's say the object actually weighs 5 grams. And if the object actually weighs 5 grams and we're getting 5 grams, then I'd say our accuracy is pretty good, because accuracy, the more accurate we are, the closer our measurement is to the true value being 5 grams in this case. Let's say the true value were 4 grams, then none of these are very accurate. And so we don't know what the true value is. And so we can't really gauge the accuracy until we're told the true value. If we're told the true value is 5 grams, then yeah, these are all 3 pretty accurate. But what's the difference between those 3 then? If all 3 of them are accurate, would you say one's more accurate than the other? 5.00 grams is more accurate than 5 grams? Not really. You know what we'd say? We'd say that these don't share the same level of precision. And the level of precision means how exacting is that measurement? How much can we pinpoint that particular measurement? And so when we have something like 5 grams, that's typically a 1 sig fig. It's kind of a wide range. And so it's like estimating the height. I'd say the height of this is about 1 meter. Would you agree? Or could you come up with a more precise? What would you estimate the height of this? A little more than a meter? And how much more than a meter? Like 1.2 meters, 1.3 meters, 1.21 meters? What would you say? And so, yeah, it depends. This is more than a meter, but we just said it's roughly a meter. Normally, if we only have 1 sig fig here, we don't know how precise that is. And so this is the rules of sig figs. When we look at a number like this, I usually take half the smallest unit of measurement. And so the unit of measurement would be 4 grams, and the next unit would be 5 grams, and the next unit would be 6 grams. So if you had something like 5.3 grams, you couldn't see it here. It would just round down to 5 grams. Or if you had something like 5.6 grams, it would round up to 6 grams. And so we only have 1 gram of precision, we say. So if we only have 1 gram of precision, what I do is I take half of that, and so we'll just say plus or minus half of that, which would be 0.5 grams. And so that gives us a range. The range would be about 4.5 to about 5.4. I'm not going to go to 5.5 because then I should round up. But I'd say, if I have something that weighs 5 grams, and that range, range of precision would be between 4.5 and 5.4 grams. Kind of a wide range. And so the same thing here. If I say that's about a meter, I'm talking anywhere from a half a meter to 1.5 meters, essentially. That would be the meter. And so that's more qualitative. It's not as quantitative. It's not as precise. If we go to the next one, the smallest unit of measurement would be 1/10 of a gram. So we can go to like 5.0, 5.1, 5.2, 4.9. And so we take half of 1/10 of a gram and we get 0.05. And so we'll just say the precision range is going to be plus or minus about 0.05. Let's see, get the pen back. Oh, there it is. And therefore, our range would be something like 4.95 to about 5.04 grams. I'm not going to go to 5.05 because then it would round to 5.1. And so what we see is a much tighter range. And so this is more precise. We can pinpoint the value within a narrower range than the previous one. Okay, and then the second one, we'll go 0.01 increments. 0.01 is called a centigram, and half a centigram is 0.005 grams. And so this would be 4.995 to about 5.004 grams. And that is going to have a much tighter or a much narrower range. So what we say is that the more sig figs there are, the more precise that measurement is. Precision and sig figs go hand in hand in this sense. And so what we're doing is we're just getting a more and more expensive balance. A balance that reads to the nearest gram is not that expensive, but if you get a centigram balance, you're talking about $200, $250. This is actually, all my numbers, I got to readjust for inflation. Pre-inflation was about $250 by a centigram balance. Then a milligram balance would be the next level. A milligram balance, like $1,000. A 1/10 of a milligram, which goes 4 decimal places, it's like $5,000. In Chem 1A, we're going to use both. We're going to use a centigram balance. This is going to give us 2 decimal places like that. And we're going to use a 1/10 of a milligram balance. The 1/10 of a milligram balance, let's see if I can get this to move, can read 4 decimal places. And so if we take a half of a tenth of a milligram, which would be 5/100th of a milligram, let's see, 0.0005. Then this is very sensitive balance. It can detect very minute changes in mass. And so this is going to go from 4.9995 all the way up to 5.00004 grams. And so very, very sensitive balance. And that very sensitive balance is very expensive, $5,000. But is it more accurate? Is this more accurate than this? Not necessarily, because accuracy deals with something else. You know, this is one way of thinking about precision. You know what accuracy is the balance. All these balances could be inaccurate. And the most common cause for this is just instrumental drift. I mean, this is why the supermarkets, they have to have regular checks to make sure that the balances are reading the correct weights. And so what they do is I think the county does this. They go around and verify it, but also they have people come in to do what? The balances in the supermarket have to be, and so a technician comes in and does a process called calibration. So accuracy, we need to, we don't know if any of these are accurate. And so accuracy requires, calibration. And so if these balances are properly calibrated, then they should be reading accurately, as accurately as possible. But there could be things that offset that. And so let's talk about another way of looking at precision and accuracy. So this is one way. And so as we go down here, we're getting to higher precision instruments. These higher precision instruments are more expensive. Usually higher precision instruments are typically more accurate too, as long as they're calibrated. But another way of thinking about precision and accuracy is via random and systematic error. Random error, normally, let's say you're going to measure this object, and let's say we take 3 measurements of this object, and let's say the true value of the object is 5 grams, and on our first weighing we get 4.95 grams. On the second we get, let's say, 5.00 grams, and on the third we might get 5.05 grams. Okay, this is weighing the same object 3 times. And so we do 3 trials here. This would be experiment A. And then let's say another student comes along and does that. So this will be student B. And they're going to do experiment A. But this student gets, let's say, 4.02 on the first weighing. On the second weighing, they get 5.13, and on the third weighing, they get 6.04 grams. And if the true mass are 5 grams, then this is pretty accurate, right? This is very accurate, and this is a little off. This is a little off. And over here, this one is the most accurate of the 3. But the other situation here is this. Since it's the same object, we expect all these masses to be the same. And so what we can say here is these 3 are in much better agreement than these 3. These are, because if this person weighted again on weighing number 4, it could be way off. Maybe it goes to 7. We don't know. And so in this context, we say, you might say the precision is the same because both of these are centigram, masses. They're weighed to the nearest centigram. But that's not the way we look at it in this case. Even though the balance is the same and it's the same precision balance, there's a difference. And the difference is the agreement between the 3 measurements. And so over here we have better agreement. And so this set of results has higher precision. And this set of results has lower precision because the agreement between individual measurements is poorer. And so this is lower precision. And so there's two ways we look at precision. One way is by the instrument itself, how many digits does it display? The other way is the agreement between individual measurements. Now, the problem is, has the balance been calibrated or not? And that could lead to a systematic error. If both student A and student B are using the same balance, which has not been calibrated, none of these are expected to be accurate. You know, let's say the true mass were 6 grams, and the balance is reading low at all times. And so, in terms of systematic error, systematic error is just a result. If the balance is always reading 1 gram too low and the true value were 6 grams, then yeah, these are all going to be reading 5 grams. You know, and although this one looks accurate, this balance is reading 1 gram too low, so that's really reading 7 grams. So systematic error is due to miscalibration, or there's one other. Not necessarily miscalibration. Calibration is good. And it's hard to screw up the calibration sometimes. Let's just say uncalibrated. Or always using the wrong technique. That is, let's say you're reading a meniscus and the person accidentally reads the meniscus not from the bottom of a water meniscus, but from the top. And if they're reading it always from the top, they're going to have a systematic error. They're always going to be reading too high. Or they're reading the meniscus too low, or that is from below or from above, not perpendicular to the meniscus. And so this would be technique error. And so, or a technique error. And it's not just some random technique error, it's a technique error that's repeated over and over again. And so, in terms of precision, we can improve precision by getting higher precision instruments, or we can improve precision by improving our technique. So let's say student B is a little bit sloppy. If they improve their technique, they might get results like this. And so that's one way to improve precision. Do you know another way of improving precision? So we can improve technique to improve precision. But do you think that's going to completely eliminate the error? No. I mean, even if you improve technique, you'll probably get it to a narrower and narrower range, but there's still going to be small fluctuations in the measurement. And so is there a way to get rid of random error? There's an easy way to get rid of systematic error. The easy way to get rid of systematic error is just calibrate the instrument or fix your technique. There turns out to be a hypothetically easy way of getting rid of random error. Do you know what the hypothetically easy way of getting rid of random error is? You do a lot of trials. And how many trials would you have to do to completely eliminate random error? Like 3 trials? As many as you can. And in fact, in theory, you would have to do an infinite number of trials. Because if you do an infinite number, then you'd predict half of them would read too high, half of them would read too low, and they'd cancel. The errors would just cancel each other out. We don't know what's going to happen in the fourth one. You know, the fourth one's going to throw it off like this person. The fourth one's going to throw it off. Right now, it averages to 5. But who knows, the fourth one might throw it off a little bit. And the same thing goes here. And so we don't know. And so what we do is we try to do as many trials as possible and then take the average. The average is going to help minimize the random error. Now, when we do this, how many trials should we do? Because if we do 1 trial, is that enough? No, 1 trial has a lot of uncertainty associated with it. And so we can't have too much confidence. If we only take one measurement, like say this person here, they only took one measurement and they got 6. Let's say the instrument's properly calibrated. Is this very accurate? No, that's way off because it's supposed to be 5. So if they did one trial here, they're way off. And you can't have that much confidence in the measurement. If we do 2 trials, it's a bit better, right? 2 trials, you're going to dramatically improve the amount of confidence you can have in the average. And 3 trials is even better. And so there's going to be a big jump in confidence in going from 1 to 2 trials and then 2 to 3 trials. How about in going from, let's say, 999 trials to 1,000? Let's say each measurement takes 2 days to make, because you have to make this stuff. And if each measurement takes 2 days, then is it worth it to go from 999 trials to 1,000? Clearly 1,000 trials is better, but is it that much better? No, the return gets smaller and smaller. So the difference between 1 and 2 is huge, but the difference between 999 and 1,000 is minimal. And so what's the best? Well, in some experiments it's easy. You can calculate, you can measure thousands of data points in minutes or seconds even. And so on some experiments you can collect 10,000 data points, no problem. On other experiments, it's quite difficult. Like for example, our sulfate analysis, it's a lot of work. Each one of these is a lot of work. And so for something like that, what's the best trade-off? Should we just do 1? It saves us a lot of work, or 2? And it turns out statisticians work this out, and the best compromise is taking 3. You know, if the experiments are difficult and it's hard to get the data, then get at least 3. Then you have something that's reasonable as far as validity, statistical analysis. And so in a lot of scientific experiments, we just take 3 measurements and then average those, and then hopefully that minimizes the random error. Now for systematic error, that's a different story. We have to look at that. All right, so we observe, and when we observe, we want to be as quantitative as possible. When we're quantitative, yes, we want exacting results, and these exacting results, we have to think, how much uncertainty do we have in these numbers, or how much confidence can we have in these numbers, and how much error do we expect in these numbers. All right. Once we take our observations, then are we done? Sometimes we have a lot of observations. For the temperatures, we didn't have that many observations, but in other experiments, we take a lot. And so what do we do next after observation? Do we go straight to the hypothesis? Yeah, we look for a pattern, and let me show you why here. So we observe nature, and then we look for patterns and trends. And so I know Petrucci has that here, but let's take a look at some data here. Come into my data table. Oh, there it is. Oh, actually, I need to talk about 2 more things before I move on. I just forgot to mention. It also, we need to know, are we measuring, usually we measure properties like color, mass, volume, this type of stuff. And we need to know, are we measuring a intensive property or an extensive property? Do you guys recall the difference between intensive and extensive? Intensive versus extensive. Oh, this is tough. So, for example, like a pound of feathers versus a pound of gold. Which one weighs more, a pound of feathers or a pound of gold? They weigh the same amount, of course. Because a pound is an intensive property or extensive property. Pound is weight. It's an extensive property. It's just going to depend on the amount. It doesn't depend on, well, it depends on the amount. And so we have a pound of each, and so therefore they're equal.
Are we talking about pound as a unit of force or mass?
A unit of weight.
Well,
Weight would be
weight
force
depends
upon
on
mass.
gravity, though.
Yeah, and so it would be weight, like, because we use, like as mentioned earlier, chemists use weight and mass interchangeably, and so it would just be the mass of the feather, basically. But a pound itself is a unit of weight. Okay, depends on the amount here. But what's different between a pound of feathers and a pound of gold? The density. And the density is independent of the amount, so it doesn't matter if we have a pound or 10 pounds or whatever. The density will be different. Speaking of densities, when we take observations, we want to make sure we make reasonable observations. So let's, qualitatively, do you know the density of water? Qualitatively, what is it? One gram per milliliter. And so that's qualitative. But if you want to be more quantitative, then we should try to take more precise and more accurate measurements. And so that's what's done in this data table here. We're going to just try to take more quantitative measurements of the density of water. And then what happens is the density of water changes with temperature. And in fact, they didn't take 3 measurements per temperature. They just took 1 measurement per temperature because there's so many temperatures here. And so I know this is impossible to read, but this is 5.0 degrees C, etc. And so they're going from temperature, let's say we go from temperature from 0 degrees C to 100 degrees C. So we're going to collect data at every tenth of a degree C. And so here are our observations. And so the next step would be to come up with a hypothesis. Do you have a hypothesis for this? Okay, so you look at the data and you look at the numbers, and can you come up with a hypothesis? So this is why I didn't do it the same as Petrucci. I inserted a couple of steps because it's too hard. I look at all that data and it's too hard. This is not the way we do it. We look at the data and it would be way too hard to come up with a hypothesis right now. But what we do is we look for patterns. And so when you look for patterns, let me blow up this one. Do you see a pattern here? Well, I see kind of a pattern. It looks like the numbers are kind of decreasing as the temperature goes up. But when I go back, it looks like the numbers are kind of increasing, And so the numbers kind of increase and then kind of decrease. And so something weird may be going on there. Do you have a hypothesis yet? And then maybe not. But what we do here in science is we do this. We do a process called data reduction. You want to? And so when we look for these patterns and trends, that's just too much data. It's overwhelming. So we try to get it in simpler terms. And what's easier to remember? Is it easier to remember that table of numbers, or is it easier to remember some kind of pattern? The pattern might be, the density went up and then went down. That's easier to remember, isn't it? And then you remember a couple of numbers. What was the peak density? What was the minimum density? The peak density was 1. The minimum density was 0.96. I know you guys can read the table, but that's what I saw. You know, actually not. It was a 0.96. Yeah, 0.96. And so we look for these patterns and trends, and this process is called data reduction. And typically, what we do when we do data reduction is we graph it. And then we try to analyze it. So data reduction and data analysis. And so let's take a look at that. So here it is. When you look at this, does it look like a linear trend or non-linear trend? Linear would be straight line, y equals mx plus b. Does it look linear or non-linear? Non-linear. And then if we blow up this first part from 0 to about 10 degrees C, it looks like it's a flat line here. But when we zoom in on that part, it isn't a flat line. Let's zoom in there and take a look. Oh, come on. There used to be a really nice graph. I'm going to just have to save it. My computer. All right, so we zoom in on the very first, and then do you see what happens here? The density increases and then decreases, and it peaks about what? At about 4 degrees Celsius here. And so this is part of data reduction. We take that huge data table and then reduce it to a graph. Here it's much easier to see the trend in the density, right? Okay, then what's the next step typically? We try to, a graph like this isn't the most concise way to define this, So we want to go from 0 to 100 degrees C. The most concise way of defining this graph and that data table is by using a mathematical equation. And so what we want to do is we want to try to fit this curve with a mathematical equation. Oh, don't tell me this is going to cost, yeah. Okay. And so this is the equation you can get by fitting that curve mathematically. And Excel can do this, and a lot of graphing packages and software packages can do this. And so we just try to fit it. And when we try to fit the curve, we want to see, does that curve fit our model? So this is our model here. And how well the curve fits our experimental data, that is the curve generated from our model, fits the actual experimental data, is usually given by R squared. Have you heard of R squared? R squared is called the correlation factor. And R squared, if R squared is 1, it's a perfect match. So the data in the table matches this mathematical equation perfectly. In science, we want R squareds that are close to 1, like 0.999, 0.998, in the high 9s. In the social sciences, they don't get as good of correlations. Like I was listening to social scientists talk, and they said, it's great if they get a correlation factor of 0.6. I was thinking 0.6, 0.68, that's garbage in science. But in the social science, human behavior is very difficult to model, so I understand that. But the standards are quite a bit different. Anyway, the R squared is quite good for this curve. But, the higher the order of the polynomial, this is a 4th order, the temperature of the 4th here. The higher the order, it's easier to fit anything. But then you start veering far away from, the physics of it. But anyway, we can fit this. And so we don't have to graph it. There are different ways. In Chem 4 and Chem 1A, we use the data table. And the way we use the data table in Chem 4 and Chem 1A is we figure out what the temperature is, and then read the density. That's what we do like in the density of water experiment in Chem 4. That's what we're going to do in the density of water experiment in Chem 1A. Sometimes we have to do an interpolation. So for example, if the density falls in between 2 points, then we'll do a linear interpolation. Assume it's linear between those and then interpolate. Sometimes we might have to extrapolate if the data table doesn't go too far. Sometimes we do graphical analysis. In a graphical analysis, we do something like this. Where did my graph go? In a graphical analysis, we just pick the temperature. Let's say it's 50, draw a straight line, and then go across here. The density is, this is density in SI units. SI unit for mass is the kilogram, and SI unit for length is the meter. And so volume is a derived unit, it's meter times meter times meter, so it's kilograms per meter cubed. And so, the 1,000 kilograms per meter cubed is 1 gram per milliliter. And so this would be 1.00. And so the density drops. So at about 50 degrees C, we have a density of about 0.985 grams per milliliter. The peak density is up here, about 1 gram per milliliter, and the lowest density is down here around 0.95, 0.958, maybe even 0.957. And so we lose about 4% density. So qualitatively, we can say that water is 1 gram per milliliter, but that's not very quantitative, right? If we want to be quantitative, then we got to get it to more sig figs, more precision. And 1 gram, yeah, maybe it's close enough. It doesn't change that much. If you say 1 gram per milliliter over the whole range, you could be off by a little more than 4% in your calculation. That is a 4% error in your calc. But it's close. All right. And so we call this, what do we call this? They call this what do they call this? An empirical equation. Empirical means what? Yeah, based off observation. So this equation just came from the ground, from observation. For the density of water as a function of temperature. You can find this equation is in our book as well. It's in one of the homework problems, and I think I signed it. So you may do a calculation based on it in the book. And we call that empirical equation, what do we call that in the scientific method? A law. And so this would be the law of the density of water. The law, typically, most laws are derived empirically, and most of them are just a simple mathematical equation defining the observations. After the law comes the
theory?
Not the theory, because the theory has to have widespread acceptance. So before it becomes a theory, we call it a hypothesis. A hypothesis is kind of like a theory, but without the widespread acceptance. And so we come up with a hypothesis. And so this requires a little bit deeper thinking. To use the law is no problem. We could use the law to make all kinds of predictions about what the density is at any temperature, or if we're given a density, we can predict what temperature it must be. And so a law we can use, and we do use, but a theory is trying to dig into things deeper. And so let me tell you what I need you to hypothesize about, and you can give me your hypothesis. Can you give me your hypothesis why water expands and then contracts, and then why 4 degrees? Why not 5? Why not 10? Why 4 degrees C? Well, why 4 degrees? Who knows why 4 degrees? It's, what science does is it doesn't tell you why. Well, maybe it might tell you why, but, what scientists do is they just observe nature, and this is how nature is observed to behave, right? And so that's the scope of science right there. And I think if we, anyway, we'll just go back to this question here. But I think it doesn't really, science just describes nature. And I think the confidence and the mistrust, well, the lack of confidence and mistrust of science is people like saying things, what science really isn't, But let me get back to this. So the hypothesis is, tell me why the volume expands, that is, the density goes down, and then at 4 degrees C, suddenly reverses course and starts to contract. That's the hypothesis. Could you have come up with a hypothesis initially? Would you have hypothesized 4 degrees Celsius? Is that a special temperature in your mind? No. And so we do these observations, we look for these patterns, and then we try to hypothesize. And so there is some hypothesis, and the hypothesis is going to involve, what do chemists do? What do chemists study? Chemists study composition, structure, and properties. So we look at this compositionally, structurally, and then try to base the properties on that. And so we might come up with ideas why it contracts and then expand. But we're not going to do that. We're going to stop here because it's okay. Have you thought about this kind of stuff for the ideal gas law, the hypothesis? No, you just use the ideal gas law, right? And that's perfectly fine. But for some things, we want to hypothesize a little deeper and try to understand a little deeper. Because if we understood the theory of this, then we could make predictions about other liquids. What other liquids, do other liquids behave like this? Do all liquids behave like this? And the temperature's there, or do some liquids just go down, or some liquids go up? That's the power of the theory. So if we really understood this at a fundamental level, and that's what a hypothesis is a description at the very fundamental level, and a theory is a widespread acceptance of that description, then we could make predictions about any other liquid, ethanol, whatever you want. And so ultimately, we want this hypothesis to evolve into a theory. And the way a hypothesis evolves into a theory is through scrutiny and testing. So I might come up with my hypothesis, and then I'll write it up, and then I'll try to submit it to a journal as a paper, maybe Nature, or maybe this has already been written about in Nature or Science. And then it's going to be sent off to the referees. The referees will go and review it and make sure that they also follow my hypothesis, and then if they are in agreement, or if they want, maybe they want additional experiments to be done, or maybe they want to send it off to other people to review, eventually it'll gain that acceptance. And when things gain that general widespread acceptance, then, and even when papers get published in Nature or Science magazine, they still can be retracted because they quite haven't gained that widespread acceptance, And so this theory. But that's not to say some theories have gained widespread acceptance and then have been further modified. So there could be additional branches here, but this is the basic process of the scientific method. And so what is the purpose of the scientific method, you say? And so there's a lot of testing that's done here. Like the laws are tested, hypotheses, laws of thermodynamics. There are people who have been testing these for centuries, trying to come up with things like perpetual motion machine. Perpetual motion machine would violate the laws of thermodynamics. I think people are selling these on eBay, perpetual motion machines, but are they really violating the laws of thermodynamics, or are they false claims? But anyway, the scientific method has worked very effectively, although it doesn't tell us certain things, like why 4 degrees C, or why this, or why that. We're just observing nature. And this has been the power of the science. It's confined to a certain space. And if it stays confined to that space, then yes, it's extremely powerful in furthering our knowledge. Nature. All right. So So the density of water is about 1. And we should know the roughly the range of densities we expect to observe. Osmium is an interesting element because do you know what's special about osmium? Yeah, this is like the densest element on the periodic table. Iridium and osmium are the 2 most dense. And how dense are they? 22. Yeah, 22. That's good. That's a good number. But maybe you don't need to know osmium. Osmium is about 22 grams per milliliter, and it's the most dense element on the periodic table. But most people remember gold. They remember water as being 1, and gold should be about what? It's less dense than osmium, but not that much less dense. And it's an easier number to remember. 20. Yeah. Why do we want to know that? Well, why we want to know that is because when we make these measurements, when we do these calculations and we're getting densities, let's say you're getting a density. This happened in Chem 1A, but it's more common in Chem 4. People come up with a density of water of 430 grams per milliliter. 430 grams per milliliter is more dense than anything that we know, except the nuclei. And so 430 grams per milliliter is ridiculous density. But if you had if you have no knowledge of what a reasonable density is, then 430 sounds reasonable, just like any other number. And so what we want is we want to memorize a few reference points, like the density of water, 1. That's very qualitative. The density of gold, 20. And gases. The density of gas would be about 0.001. Or we don't like 0.00, so instead we say 1 gram per liter, roughly.
The density of water is exactly 1, not approximately 1, right? Because that's how we define the measurement.
No, density of water is not exactly 1. The density of water is approximately 1, and it changes with temperature. So it depends on what the temperature is. So for example, if the temperature is close to the boiling point of water, then it's more like 0.96. If it's 0.96, then that's 4% off. And so this is, I want you to memorize the density of water, but you have to keep in mind that it's qualitative. But the closer we are to 4 degrees C, the more quantitative it is, the more precise and more accurate it is. I shouldn't say precise because it's still 1 sig big, but we can be more precise. So the closer we are to 4 degrees, we can go maybe 1.0, 1.00 in terms of the density of water. The further we are away from 4 degrees C, the less precise we can be. So let's say in the range from about 0 to room temperature or a little above room temperature, we can say the density of water is 1.00. If we go above room temperature, then maybe we can go a little above room temperature, we could say 1.0. If we go a lot above room temperature, then we can just say 1, and then we'd be safe. So we talked about systematic, random errors, precision, accuracy. Here, this is a 1/10 of a gram balance. We don't have any 1/10 of a gram balances in our lab. We have centigram balances, or 100th of a gram balances. And this is a 1/10 of a milligram balance. So the first digit here is 1/10 of a gram, 100th of a gram, 1,000th of a gram, 10,000th of a gram. 10,000th of a gram is called a 1/10 of a milligram because this is a milligram digit here. So this would be 7 milligrams here. And this would be 0.8, 7.8 milligrams. In other words, this in milligrams would be 10,497.8 milligrams. And so this is called a 1/10 of a milligram balance. These are like 5,000 pre-inflation. And we have a bunch of these. And so we'll have a bunch of these and then some of those centigram balances, which are in between those two. Sig figs we talked about a little bit. You can review the sig figs. But what I want to do is, at the beginning we're talking about density and calculation, density percent and calculation. So I want to go to some calculation. So we're going to take a look at, first actually a conceptual problem on sig figs, and then some calculations next. So 67 wasn't on Mastering Chem, and so I want to just cover this here. This is from your book, in chapter 1. According to the rules on significant figures, the product of the measured quantity is 99.9 meters. So how many sig figs is that? 3. And the uncertain digit, the last digit is the uncertain digit. And there, we're going to have some spread. So this is not right on 99.9. It's between, let's say, 99.85 and 99.94. Right? And so there's some uncertainty in this last digit here. And so the uncertain digit is in the tenth, or in other words, it's roughly about 1 part in 1,000. We can call this 1,000. So 1 in 1,000 uncertainty. Over here, times 1.008, how many sig figs is that? Now the uncertain digit here is not in tenth of a meter, hundredth of a meter, 1,000. The uncertainty is in 1,000th of a meter, but another way of thinking about the uncertainty is if we have 1 part of uncertainty, this 8, it might be a 7, it might be a 9. This 1 part in 1,000. So both of these are about 1 part in 1,000, even though the uncertain digit is in a different decimal place. Does that make sense? And so we have about 1 part in 1,000 here, 1 part in 1,000 uncertainty. According to the sig figs, we have 3 sig figs and 4 sig figs. Our final answer should have 3 sig figs. But when you look at the uncertainty here, let's say the uncertain digit here is 1. So there's going to be uncertainty. It might be 100, it might be 102. There's about 1 digit of uncertainty there per how many total? Per 100. And so this is correct according to the rules of sig figs, yet in this case, it would be more appropriate to express the result of 4 significant figures. That is 100.7 square meters. Why?
It's more precise.
It's more precise, but yeah, obviously, why not just express it with more and more digits here? If you're using it's more precise as an argument, then I'll just say, well, add another digit. That's even more precise. Add another digit, but are we allowed to? Not according to the rules for sig figs. We're not allowed to. We're not even allowed to add this according to the rules of sig figs.
I'm pretty sure it's because when we use 1.008 meters, that has 4 sig figs, and since the uncertainty is in the 4th sig fig, adding any precision beyond that is pretty meaningless in the final estimate because we have.
Yeah, so we don't want to go beyond the 4th,
Yeah.
but why are we going beyond the 3rd?
Because of 1.008.
No, we got to go because this has greater uncertainty here than that. And so why are we adding the 3rd? And the reason we're adding the 3rd is because of this. The sig figs. The reason we do sig figs and we pay attention to the rules for sig figs, multiplication, division, addition, and subtraction rules for sig figs, is because they're easy. When you go higher in science, you stop using sig fig rules. You stop using sig fig rules and you do something called propagation of errors. Propagation of errors, first you learn it based on calculus, and then you might do an algebraic approach. So some classes, like in physics, will do an algebraic approach to propagation of errors. But we don't do it because we figure, in chemistry, we figure you're going to get it later. But in propagation of errors, we look at it as far as a percentage. What is the percentage uncertainty here? It's 1 part in 1,000. What is the percentage uncertainty here? 1 part in 1,000. What should be the percentage uncertainty in our final answer? About 1 part per 1,000. So this is why we do it. When you do propagation errors, it's essentially taking those percentages and adding them up. And so it'd be like 2 parts per 1,000. Yeah. All right. I think the main or most important thing to get from chapter 1 is problem solving, and that is the conversion factor method or dimensional analysis method of problem solving, as well as some of the the conceptual stuff. Scientific method is important, obviously. But let's take a look at a challenging problem. the end of chapter problems, you have the regular exercises, and then you have the challenging problems, that is the advanced exercises. So this is one of the advanced exercises. We'll take a look at this. And this is number 75 in the homework. I didn't assign this one because it wasn't in Mastering Chem, it wasn't available. Otherwise I would have assigned it. So let's take a look at this. In the United States, the volume of irrigation water is usually expressed in acre feet. 1 acre foot is the volume of water sufficient to cover 1 acre of land. So they measure the area of land by acres. So you might have half an acre, quarter acre, tenth of an acre, etc. And what is an acre? 1 square mile is defined as 640 acres. This is by definition, so this is an exact conversion factor. So if you had 640 acres of land, you'd have 1 square mile of land. And then if we submerge that land in 1 foot of water, then we have an acre foot of water. That is 1 acre of land submerged by 1 foot of water. Okay, they give us this other conversion factor here, which is 1 mile is equivalent to 5,280 feet. This is also by definition, so this is exact. Both of these are exact. The principal lake in the California Water Project is Lake Oroville. Whose water storage capacity is listed as 3.54 times 10 to the 6 acre feet, or 3.54 million acre feet. Express the volume of Lake Oroville in cubic feet. So oftentimes we have these what we call composite units. Composite units, let me give you an example of a composite unit. This is a common one, joules per gram degree C. Have you seen that unit before? Joules per gram degree C. And you've probably seen this in this. Q is equal to MC delta T. Have you recalled using this equation before? Yeah. And C has units of joules per gram degree C. Joules is a unit of heat. And in other words, we can use dimensional analysis to solve this. So, for example, if we have joules per gram degree C, we can cancel out the joules by multiplying by mass in grams. So if we have mass in grams, the grams in the mass will cancel the grams here in our unit. And the degree C can be canceled out by delta T. And so if we have delta T here in degree C, those will cancel out too. And that leaves us with joules. And joules would be heat or energy, Q. And so sometimes we'll have composite units like this. Well, an acre foot is a composite unit. And so we can, just cancel out them individually. We don't have to cancel them out together. And so, or we can cancel them out together. That's possible as well if we have the conversion factor. So we're going to start off with an extensive property. These are intensive. 640 acres is equivalent to 1 square mile, intensive. 1 mile is equal to 5,280 feet, that's intensive. All the conversion factors are intensive. Sometimes we start off with an intensive property because we want to go from, let's say, miles per hour to kilometers per second or something like that. But most of the time we're going to start off with an extensive property. This is an extensive property here, 3.54 times 10 to the 6 acre feet. The volume depends on the lake itself. And that's going to be an extensive property, and we'll start with that. And so 3.54 times 10 to the 6 acres times foot. Now, I want to go to cubic feet, and so what I need to do is I want to keep this foot here, but I want to get rid of the acre. And so to get rid of the acre, I'll try to cancel it out. And when I try to cancel it out, I try to come up with some ratio here that I can use to do that. And the ratio here is just going to be 640 acres per 1 square mile. And that just comes from this conversion factor here. And I'm just going to cancel out just only the acre part of acre feet and leave the feet. And so now what I have is feet times miles squared. Well, I don't want feet times miles squared. And so what I want to do is I want to get rid of miles, but I don't know any conversion factors that get rid of miles. But I do know that if I square the whole thing, I can get miles squared. And so I'm going to relate miles to feet here. and that is there's 5,280 feet per 1 mile, and then square everything in there. So that would be 5,280 squared, feet squared, miles squared. And if that's the case, the mile squared here cancels out this mile squared, and that leaves me the foot squared. So I'm going to have a foot times a foot squared. A foot times a foot squared gives us a foot cubed. And so that's what I want. And so I'm just going to plug this into the calculator and see what I get. This is going to be 3.54 times 10 to the 6th divided by 640. See if you get the same number, times 5,280 squared. And this is what I get. I got 1.54. Actually, how many digits do I need to write? And so that depends on how many sig figs I'm allowed. How many sig figs in 3.54 times 10 to the 6th? 3. How many sig figs here? Infinite. This is by definition. How many sig figs here? Infinite. And so I'm allowed 3 sig figs here. But I don't want you to write 3 sig figs. I want you to carry 1 extra. So I want to see what the drop digit is. So what I'm going to do is I'm going to go 1 more than 3. And so I'll do 1.542. That gives me 4 sig figs. I'm not allowed 4 sig figs according to the rules for sig figs, but I'm just going to go ahead and do that. And this is going to be times 10 to 11. And then I'm going to add one more step here where I'm going to round it. And is this going to round down or up or what? Or just stay, it's just going to stay at 1.54. And so I'm going to get 1.54 times 10 to the 11th cubic feet of H2O, water. Uh-huh. Because I have this leftover foot here that I didn't cancel. And then this one, I have to square everything in here. So this is going to be foot squared here. So foot squared times foot is going to give me foot cubed. And that's how I got it. Is that what you guys got? 1.54 times 10 to the 11th? That seems like a reasonable answer because, you know, acre foot's huge, a cubic foot's tiny, so compared to an acre foot. All right, let's go to cubic meter. So I just start this problem over again here, and I'm going to start it at 3.54 times 10 to the 6th acre feet, and I'm probably going to do the same thing here. Initially, I'm going to get rid of acres, so 640 acres per square mile, and that gets rid of just the acre part of that. And then I want to get rid of the square mile, so 5,280 feet per mile, and then square the entire thing. All right, when I do that, the miles square cancel, but I have to watch out because now what are the units? The units are going to be foot times foot squared, which is going to be foot cubed. So what I need to do is I need to get rid of feet. And so I can go from feet to inches, or I can go from feet to miles. Which one should I take? Feet to inches. So I'm going to go 1 foot to 12 inches. And then what I'm going to do here is square this or cube this. I got to cube this. I got to cube this because now I got to get rid of, let's see, can I get this pen to change here? I got to get rid of this foot that's left over here and this foot squared that's up here. And so doing that is going to get rid of the foot cubed. Now I have inches, so I can go from inches to feet. Well, that would be going in circles. Or I can go inches to centimeters. So I'm going to go inches to centimeters. So 1 inch is 2.54 centimeters. And then I'm going to cube the whole thing. And so that's going to get rid of cubic inches here and leave us with cubic centimeters. And from centimeters I could go to meters. And so 1 meter is equivalent to 100 centimeters, and then I'm going to cube this whole thing. And that's going to get rid of the centimeters cubed here and leave me with cubic meters, which is what I want. Uh-huh.
What is that third parentheses you wrote, the middle one? Sorry.
This one here,
Yes.
12 inches per 1 foot.
Thank you.
How many sig figs am I allowed here? So this is 3 sig figs, infinite, infinite, this one, infinite, this one, infinite. Because this one's tricky, it's exactly 2.54. This one, infinite, so I'm allowed 3 sig figs again. And so let me punch this out, and you punch this out too and tell me what you get. 3.54 times 10 to the 6 divided by 640 times 5280 squared times 12 cubed times 2.54 cubed. Oops, I made a mistake. I forgot to close me. Times 2.54 cubed divided by 100 cubed. And I get, so I'm allowed 3 sig figs, and so I'm going to carry 4 here. I get 4.366 times 10 to the 9. So 4.366 billion cubic meters. And so let's round this to 3 sig figs. This should round to what? 4.37 billion, that is 10 to the 9 cubic meters of water. Is that what you guys got? Okay, good. Going to US gallons, we're going to need, like all these we used exact conversion factors, but going to US gallons, we're going to have to use some approximate conversion factors, but we'll try to be as precise as possible. And so the conversion factors that we're going to need for this extra are the conversion from centimeters cubed to milliliters. 1 centimeter cubed is defined as 1 milliliter. They're the same thing. So cubic centimeter and a milliliter are the same. And then we're going to need this. 1 gallon is equivalent to 3.785 liters. This is only 4 sig figs here. This is exact. And so that's infinite sig figs. But if we have 4 sig figs here, it's not going to limit our answer. We're still going to get 3 sig figs in our answer. If you used 1 gallon is equal to 4 liters, that would be an error, a rounding error. All right, why don't you do this one at home? Because I want to talk about one other problem. I only have, what, 2 minutes left? I think. Okay, the other problem I want to talk about is I think it booted me out. Actually, I'm not going to find that problem, but let me just briefly mention this so you can think about it overnight. And that is, we talked about, we're going to talk about density, and we're also going to be talking about percent. And usually, when we talk about percent, we often refer to percent composition. So let's say we have percent of A. Percent of A would be grams of A over total grams times 100%. This works well, you know, for certain scenarios. An example of this where it works pretty well is, let's say you have half a gram of A and you have 1.0 grams total. And so what is the percent of A in that? It's going to be 50% A. But let's do another example. Let's say you have 0.00000 0.005 grams of A in 1.0 grams total. And then when we multiply this by 100%, what is the percent going to be? It's going to be 0.00005%. Now, 0.00005% is kind of a small percentage, isn't it? There's very little A in this. And so can we just ignore it and call it 0? No, we don't ignore it and call it 0. But what we typically do is we don't use percent. We use something else that's very similar to percent. We maybe use ppm. And so if we did this in terms of ppm, rather than multiplying it by 100%, we'd multiply it by a million ppm. So let's do the same thing. We have 6 zeros here, 0.0000005 grams of A per 1 gram total. But now I'm going to convert it into ppm by multiplying it by 1 million ppm. And so if I do this, then I'm going to convert this to 0.5 ppm A. So 0.5 ppm versus 0.00005% is a lot easier to deal with. And so sometimes we might go to ppb. And so in the next problem I'm going to just do one more problem from chapter 1 tomorrow. We're going to look at ppm, and we're going to look at conversion factors in more detail, and some more composite ones, but a little bit trickier. Okay? All right, thanks. All right. Uh-huh. A lot of conversion factors I'll give you, but some you have to have memorized. Usually the definition ones I like you to memorize. But most of those you have like inches to feet. Inches to feet, that kind of thing. You know, feet to yards. The other ones, like liters to gallons, you don't have to memorize. Milliliters to liters, you have to have memorized.
Where does the homework, where do we find the homework problems that we're supposed to do?
On Mastering Chem.
It's just,
Are you registered or are you waitlisted?
I'm registered. I'm just trying to figure out, because when I go to Mastering Chem, it says it wants me to find a link on Canvas or something.
No.
Do I not need to do that?
You don't need to do that. When it says, do you have LMS? Say no.
Okay.
And then it'll take you. Yeah, we're not going to link it to Canvas.
Okay.
So just, and then just enter the course. I forgot to mention that to everybody, but don't say you have Canvas, because we're not going to link them together. It's still. I had 2 no-shows today, so let me see what happened to them tomorrow. You're on the official wait list?
Yes.
Okay. Yeah, come tomorrow.
I think my question was the same as yours.
Yeah, come tomorrow and I'll know. I had 2 no-shows today, so we'll see. Two no-shows who are registered.
It's on 5th.
You're 5th on the wait list?
Yeah.
I don't know. We'll see tomorrow if more people decide. I don't know if they decided to drop and not come anymore. It's hard to say. Or if somebody's going to drop today, we don't know.
So just keep going.
You can keep coming and then see what happens. Yeah.
Thank you.
Any handouts that I missed yesterday?
You weren't here yesterday?
No, and today I got kind of lost, so I showed up late.
You missed the first day
Yeah.
of class. Be careful. Did you send me an email?
Yeah, I sent you 2 because I woke up sick.
Okay.
Plus that my family and I were like,
Oh, that's
on
right.
vacation.
Okay, so you had the vomiting or whatever, was
Yeah.
that? Okay. The handout you missed was this one. Today is Tuesday, yeah. So fill this one out and give it back to me.
Okay, thank you.
Okay, well, what's your name?
It's Brent.
Brent? All right, I did take attendance, so I didn't miss it. Okay. Yeah. And the class is full, and then there's a wait list on top of that. And you're not on the wait list, or are you on the wait list? No. Yeah, and the wait list has, let me see. A wait list has quite a few people on it. And so it doesn't look good for getting. You'd probably look for different options, maybe the night class or something. I mean, you can fill this out and give it to me if you want. And then
And what about the morning class?
morning class is the same situation. It's full plus wait list. And so maybe night class, or you've had Chem 4. Did you take Chem 4
Yes.
here? Yeah. You could see if the night instructors are willing to take extras.
Mhm.
You know, I think the class is meeting tonight,
Okay.
6 or something, 5 or 6.
Uh-huh.
See if they have space. But at this rate here, it's kind of unlikely that many people will stop coming to add everybody on the wait list. And so a lot of people who are already on the official wait list may not get in, most likely won't get in. But we'll see. Yeah, I mean, you could give that to me and I'll add you on top of everybody else.
Okay.
Yeah.
When I tried enrolling in the mastering MyChem, it asked for a code, but I'm not sure where to put it or where to get the code.
There's not. They should ask you for the instructor ID.
Yeah,
Do you put that in?
I don't have access to that ID.
No, the instructor, the class ID. Do you have the class ID?
Where
Should-
do I find that?
It's in the link on Canvas. Here, I'll show.
I don't have you on campus. I'm on the wait list.
Oh, that's right. Did you get the email I sent out?
No.
Are you on the official wait list, or
Yes, I'm number 2.
take a look and check your email and see if you got the email from me and the class code
Okay.
on the email.
All right, I'll take another look. Thank you.
Hi.
Maybe a Luke, I was wondering that's emailing you before.
I'm sorry.
Maybe it's gonna be a Luke that makes it.
Oh, okay.
Yeah.
That's right. You're gonna miss the
September 9th. Yeah, I was just
September
asking.
9th. Yeah.
Yeah.
I'm thinking the only thing you could do is that's Monday, correct?
Yeah, it's Monday.
So what you can do is on Wednesday, you can try to finish both parts, Monday and Wednesday. So that just means you have to work quickly,
Oh, okay.
or you might be one day behind. But you can start on, you probably can start on Wednesday.
Oh,
That's
okay.
most likely what we're gonna do, because are you gonna be out all day on Monday?
Yeah, it's
Oh.
from 8 to 4:30. But for
Oh.
Wednesday, when you say like do both parts, like
Yeah,
and
try
all
to
that
do,
class?
or you're gonna just start it. It's okay because we can break up the lab and squeeze in parts of it. So
okay.
while other people are working on the filtration and that, you'll be doing the first part. And so you have to come in prepared
Oh,
for
okay.
that.
Is it
Most
all-
likely,
Okay.
unless I can think of something else. If there's some other instructor doing it around the same time, you can check with the stockroom. Then you can probably start with them. So
Oh.
you're in sequence. But I think the labs are all full, so
Uh,
you probably aren't going to be able to do it.
yeah. Is it possible I can like come in like a bit earlier to class time that day and get started early, or?
On Wednesday?
Yeah.
Yeah, you can come in. What are you? Well, it depends on the space again too, because it's probably going to be crowded. But if there's space, you can come in earlier. You can come in the what we say is the morning lab.
Morning lab?
Yeah,
Oh, okay.
morning lab is from like probably going to start the actual work from 10:45.
10:45.
Yeah, and
Oh.
so that would be better if you come in on that day and
Oh.
start.
Alright. Is it okay if I like write that down right now?
Yeah.
Thank you. And it would be in the same classroom. It would be 165, or
Yeah,
Which is
same
fine.
classroom, exactly, yeah.
165.
From 10:45 on.
Oh, 10:45.
Do you have a class during that time, or?
No,
free.
it's
Oh,
just
then you're-
my first class today, so I'll be able to make it.
Okay, that's good.
I also had another question about the
Uh-huh.
lesson today.
Uh-huh.
I just want to go verify. So when we're going over quantitative and qualitative
Uh-huh.
measurements,
Uh-huh.
I wrote down that qualitative were precision and random error, or precision error, random error were part of like the qualitative measurements, and
No. The qualitative, treat these separately. Like,
Yeah.
and you don't have to connect them, but qualitative is just approximate.
approximate.
Quantitative is precise.
Precise.
Yeah.
Okay.
Yeah.
Oh, I wrote this down wrong. Wait, so quantitative was approximate?
Qualitative, approximate, quantitative, precise.
Oh, okay. And then another question for when we're doing this, observation, it went from apparent to trends to law to hypothesis to theory.
Mhm.
I was wondering what law specifically was.
Law is any kind of mathematical equation that kind of defines it, or pattern, some pattern that keeps reproducing itself.
Oh.
That,
Wait,
yeah, so actually I'll talk more about the laws, but a law is just something that is a really consistent pattern.
Oh, okay.
That's all a law is, and if you have a consistent pattern, it's nice to represent that consistent pattern mathematically.
Oh, okay. So with pattern and
Mhm.
trends, just be kind of like noticing that there's a change, and then the law would be like blatantly.
What kind of change would you have? Were you here in class today? Oh, I'll give your question though. Was that it for the question, or?
Oh, I'll get my pen right now. Sorry.
You just came at the end of class.
Yeah, because I was checking it with the other professor, but he didn't.
Keep checking with the other professor, because, I mean, it's another good topic. Unfortunately, they need to add more sections for money. I don't know why they don't add more sections, but it happens every semester that people don't get in, and then they have to delay things one semester. So if you can't get in, we'll try the night class, but if you can't get in, maybe take some JE classes or something to get those out of the way. You know, try to figure, or try another school, you know, Harbor or one of the other schools, you know, might have room, but it's hard to say. But it's looking pretty slim, the chances of getting in on this, but I'll keep you, I mean, you can show up and see if there's any space tomorrow if you want, but I'll keep it.
Thank you.
Sure.
Sorry, I just want to clarify the
Yeah.
first question one more time.
All right.
It was qualitative that was approximate?
Yeah, qualitative is approximate, quantitative is exact, exacting, precise, not exact, just but more precise.
And qualitative had accuracy and systemic error? Or I'm not sure if I was like understanding it correct.
Qualitative can have both.
Both? Both
Yeah,
accuracy.
but you don't associate. You don't have to connect them.
Oh, okay.
Just qualitative versus quantitative. That's it.
Okay. Okay. And then those are the questions I had for this lesson.
Okay.
For the labs,
Mhm.
you mentioned that there was a notebook that was like a sealed binder.
Mm-hmm.
And it was in the bookstore.
Mhm.
Where was it again? It was
In the engineering section
Oh,
of the bookstore, it's a quad-ruled notebook with sewn binding.
Okay. Do you have like a picture of what it looks like? 'Cause
Yeah.
I went yesterday. I couldn't find it. But I don't know if they just like sold out of it or.
That's possible. They might have sold out of it.
Yeah.
Let me see if I can find a picture of it first. Just show you what it looks like. And this is the engineering section of the library here.
Oh.
You know, and shoot, I had a picture of it, but it's gone. It's $2.99. Maybe I accidentally deleted it. It's weird. Yeah, unfortunately, I don't have it. But it's just a light brown cover.
Right, yeah.
cartridges. They have some with this black and white cover like this,
Yeah.
but this one is more. This is it. EnviroNote. This is what they have. It's kind of this. It's more brown in
More
tone,
brown.
but it's the same. It's the same company. EnviroNotes, quad-ruled.
Oh, okay. Okay.
And this has this black tape on the side here. It's $2.99.
$2.99.
It's on like the third shelf down or something like that. It's around this level on the shelf. Okay.
Okay.
You'll see it's $2.99 EnviroNotes, quad-ruled 80 sheets.
Okay.
Okay.
And then I
Oh,
had like
wow.
one Dave to go ask also. I was wondering if I could take a picture of the calculator.
Yeah. Yeah. You can.
Yeah. Thank you.
You can take a picture of this too.
Thank you.
It's cheaper in the bookstore. It's only $2.99.
Yeah. That's how like it was like that with the folders and everything else as well.
Oh, good.
Yeah. Oh, here you go. Thank
Okay,
you.
sure. This is a good calculator.
Yeah.
It's not that expensive. I bought this at Target, but you can get it online.
Remember
Or
that
Amazon.
Target? It just looks simpler. There was just when I saw it on Amazon, I had like a writing board on the side, but
Okay. I'll check that out. All right. Was there any other questions? Or?
No, no, that was
Okay.
all.
Okay. Cool.
thank you.
Thanks. You too.